Hello, and welcome to the IU College Insider Podcast, a collaboration between the College of Arts and Sciences at Indiana University Bloomington and Indiana Public Media. Today's conversation explores a technology that could change our world, quantum computing. What is quantum computing, and how might it change everything? I'm Caroline Jarrold, Associate Dean for Natural and Mathematical Sciences and Research. Joining me today are Srini Iyengar, who is a professor of chemistry in the college. We also have IU alumnus Jim Clarke, who is the Director of Quantum Hardware at Intel Corporation. Welcome to you both. Okay, so let's put the first question to you, Jim, and thank you so much for joining us from your lab at Intel in Oregon. How would you explain quantum mechanics to a non-scientific audience?
First of all, there's a famous physicist, Richard Feynman, who worked on the Manhattan Project. And he once said that if you can't explain quantum mechanics to a 6-year-old, you don't understand quantum mechanics. And so that's probably the goal here. I like to describe quantum mechanics and quantum computing using a coin. I have a commemorative souvenir Indiana coin here. And when that coin is in my palm, it's heads or tails. It's one or the other. If this was a classical computer, it would be a bit of information of 0 or 1. But when I flip the coin, or when it's spinning on a table, and I say, what state is that coin in? You might say, well, it's heads and tails at the same time. This is the quantum principle of superposition. And if I had 2 coins spinning on a table or in the air, it would represent 4 states, both heads, both tails, tails and heads and tails. If I had 3 coins spinning, 8 states, it's exponential. If I had 300 coins spinning on a table, I could represent more possible combinations than there are atoms in the universe. Now, if we can operate on these coins or control these coins in some sort of coherent manner, we can make use of all those states, and the computational power using quantum mechanics would be enormous.
Right. And Srini, when we think of regular or classical computers, we think of bits and bytes, ones and zeros. So can you explain to us the difference between a regular computer and bits and bytes and qubits in a quantum computer?
So, very nice. Let's go back and look at the analogy that Jim just talked about. And we have a heads and a tails in a coin. I'm going to arbitrarily call the heads as a 0 and the tails as a 1. So now let's translate what Jim just said to 2 coins. Then the 4 states that he mentioned now become 0, 0, 0, 1, 1, 0, and 1, 1. So when you toss 2 coins up in the air, okay, you actually have 4 things happening simultaneously at one time. A classical computer can only do one of those 4 things. So imagine now you have 300 such coins. These are not coins really now because they're more abstract objects. They're actually quantum information, so they're quantum bits now, right? They're not 0, they're not 1, they're 0 and 1 at the same time. So they are called qubits, the quantum bits. That's what they are. So now you have 300 coins or 300 qubits flipping around in space at the same time. A classical analog will be one of those 2 to the power of 300. It's an exponential number of states. Okay, one of those, okay, occurring in a classical computer. So a classical computer will be 1 over 2 to the power of 300 times slower. So the quantum computer can simultaneously do 2 to the power of 300 tasks at the same time, presumably. Okay, I add presumably because there's still a lot of debate in this particular idea. So this is what the qubit is. Now you have a lot of these qubits are now being able to talk to each other, and that's the beauty of quantum mechanics. And there's a concept called entanglement. These qubits are now together, flipping together, so to say.
So, Jim, in your quantum computers, you don't have coins tossing around. What is actually the qubit? What does the qubit look like?
There are many ways to make a qubit. You could have entangled photons, You could optical photons, you could have entangled microwave photons, which are used in superconducting qubits. At Intel, we're studying what's known as a spin qubit in silicon, and essentially we're making use of the spin of a single electron to encode the 0 or the 1 of the quantum bit of information. So our devices look a lot like the humble transistor that we've been using now for decades, but we're controlling it at the single electron level.
And is there an easy way to explain entanglement?
Actually, Albert Einstein called it spooky action at a distance. I think he was somewhat skeptical of entanglement. But the best way to say it is if I have two electrons that are entangled close together, and then I separate them by some distance, and I operate on the first electron, the second electron will sense it. It's a very hard concept to think about from a classical sense. But it's basically that I'll call it the wave function, to be precise, of the electron is sensed by the other electron. And that doesn't go to 0, it approaches 0. And you can basically, with one electron or one photon separated from the other qubit, they can sense each other, even at a small amount.
And for our listeners, a photon is a quantum of light. It's the smallest amount of light you can possibly have.
Thank you.
Okay, and Jim, when we think of quantum computing, first, how do classical computers and supercomputers work, and at what point do they reach their limits?
Well, as Srini highlighted, in using coins as an analogy, if you had 50 spinning coins, you would have the 2 to the 50 different combinations. And that is more different states than even the largest supercomputer can process. So even a modest-sized quantum computer would outpace a supercomputer in terms of processing power. But these quantum computers require not only the quantum chip or the quantum processor, but usually control processors to control the actual bits, and then computers to process information. These computers are going to be huge. They're going to be supercomputers. So a quantum computer is going to have a fleet of classical computers and probably multiple supercomputers in order to process the information. So quantum computers will never replace classical computing. They'll work in tandem.
Jim, can you tell us what a quantum computer looks like?
They can take many forms. Perhaps the most common form is built inside a dilution refrigerator. These little bits of information are very fragile. Imagine a spinning coin on a table. That coin eventually falls over. In a relatively short time, that's a loss of information. And the same thing happens with quantum information. And so we have to keep it very cold. You see a bit of an example behind me where that is part of a dilution refrigerator. These are the size of a 55-gallon drum, or for Indiana students, the size of a keg of beer. And inside of them, they have basically what looks like a chandelier of different layers. They're just like a conventional refrigerator in terms of cooling, but they use a mixture of 2 isotopes of helium. And with that, they can get down to 10 millikelvin, which is a fraction of a degree above absolute zero, or 250 times colder than deep space even. And so then you put your device at the inside this fridge and connect it to the outside world through wires. And it's usually a freestanding system, and companies all around the world have these.
So Srini, Jim said that quantum computers and supercomputers or conventional computers will always be working in tandem. Can you give us a few real-world examples of how coupling the quantum computer with supercomputers or conventional computers will really expand the capabilities in a meaningful way?
So it's a very interesting question. There are many ideas involved here, so let's just break it apart. So one, at the first level, we want to talk about a classical computer that's observing a quantum phenomenon that's occurring in a quantum computer. So again, I really like this spinning coin analogy. So let's take that. I got now 2 spinning coins, all right? and they are both mid-air. They're both rotating. Now, while they're rotating, I'm able to say, okay, this spinning coin on the left, please don't turn right, please turn left. And as it is turning left, I tell the right spinning coin to turn the other way. All right. So now my processing of these coins is telling these two things to do different things, but then they are connected. All right. So that's where the idea of entanglement comes in now. The two spinning coins are now going to do something in a way that is connected to each other. Who is doing that? Me. I'm a classical person. So a classical observer is trying to control the quantum system. That's one way in which these classical supercomputers come in. Obviously, you need a supercomputer because it needs to be able to do many, many different things at the same time to control the quantum system. The second way is that we also believe that when problems become very, very complex, it might be required that we might have a stream of classical computers and a stream of quantum computers working together in parallel to solve a very hard problem, such as protein folding or some other, or weather prediction. Okay, so these are really hard problems that are encryption, all right, breaking RSAs, so to say. Yeah. These are all really hard problems which are dreams, right? We don't know if they will happen, but these are potential problems, but they will all come about, and classical and quantum computing will have to play an integral role together to make this happen. So many different forms in which classical and quantum computers can talk to each other.
So, Jim, you mentioned that your quantum computer platform requires ultra-low temperatures. Can you tell us about some of the other obstacles to quantum computing? And what is the holy grail of the industry? What would be seen as a breakthrough?
The first big grail of the industry would be something called quantum supremacy or quantum advantage, where a quantum computer can do something that no supercomputer can do. But one step further than that would be a quantum computer can do something useful that would serve you or I that a supercomputer can't do. We'll start to see quantum advantage in a more academic or theoretical sense over the next couple of years, but we're probably a few years away from doing something meaningful to society with a quantum computer. There are challenges in the entire system, both in making the chips, wiring the qubits, controlling the qubits, and then developing the software. When I think of what keeps me awake at night, it's probably not the quantum chip. There's a lot of chemistry in that quantum chip, and I learned a heck of a lot of chemistry at Indiana, so I actually feel reasonably confident about that. What worries me the most is all the wiring. You have all these qubits, which are very unique. All the qubits have personalities, and you essentially have to connect the wiring from these thousands, millions of qubits all the way outside. So it becomes a bit of a wiring problem to me. And that's the biggest challenge that keeps me awake at night, is how to control and connect many, many qubits, each with their own personality.
You mentioned your time in chemistry here at IU. Can you tell us a little bit about how your education at IU prepared you to meet these challenges?
Yeah, you break things down to the physical level. Quantum mechanics is often thought to be more physics than chemistry, but understanding how molecules react, that's chemistry. Understanding how you make wires, that's electrochemistry. Understanding how bonds break and form when they're reacting, that can also be organic chemistry. And the undergraduate curriculum at Indiana was really fantastic. This was, of course, 30 years ago, and gave me the fundamentals. But more than that, it gives you the fundamentals, but Indiana helped give me the curiosity to go and say, here's a problem that I don't understand. How can I apply my fundamentals so that when I walk into a problem, I'm not completely in the dark and can make significant progress. And that's the way I approach most of the chemistry problems here.
Srini, a lot of your work involves quantum simulations. Can you tell us about quantum simulation in chemistry and why it's so important and why it's so challenging?
Yes. So before we go there, there's something that is pretty useful to emphasize. Chemistry is the biggest proof of quantum mechanics. So this is the 101st year of quantum mechanics. 2025 was the 100th year of quantum mechanics. In the last 101 years, we have discovered that molecules are in fact quantum objects. The molecules have got electrons, which are simultaneously present in multiple places at the same time. They also have nuclei, and nuclei are also more quantum mechanical. So hydrogen nuclei are quantum mechanical, more so than other nuclei. So the molecules are basically quantum boxes. And so they actually simulate quantum mechanics for you by themselves, right? You don't have to do anything. The molecule is living, standing in front of you. We are breathing some of them, right? They're all quantum objects, okay? So now, what is quantum simulation? The problem is that we still cannot understand a lot of complex processes in chemistry. Many of the reactions that Jim mentioned are still quite hard to understand. Can we simulate one quantum system, that is a molecule, using another controllable quantum system? Okay, so now an example from my own work with collaborators here at Indiana, Phil Risham in the physics department and Amar Sabri in computer science. In Phil's lab, we have a set of ytterbium ions which now act as qubits. Now we are able to make the ytterbium ions, an array of them, okay, now behave like a hydrogen bond that is occurring in some large system. So you have molecules with bonds in them, and we are able to make these ytterbium ions behave like those more complex chemical systems. And that's an example of quantum simulation. We're now also in collaboration with many other entities, such as Sandia National Lab and IonQ, where we also simulate these things. So quantum simulation essentially allows you to simulate, as the word suggests, okay, a quantum system, which now is a molecule. A molecule is a quantum system, using another key is controllable, and that is where the wiring that Jim is talking about comes into question. How do you control it with extreme care? And very complex wiring is involved in the set of hardware that they develop at Intel, and in the set of hardware that's developed at IU, there are photons involved that interconnect these qubits.
So ytterbium is a lanthanide metal.
Mm-hmm.
And so you have these several atoms in some setting. You can't just have 5 or 6 ytterbium ions sitting on your countertop.
Yes.
So what has to happen in order to use these single atoms, atomic ions, as qubits?
Yes, this is an extremely good question. So now let's understand ytterbium is a lanthanide. And the specific kind of ytterbium ions we are interested in using is ytterbium plus. Ytterbium plus is a one-electron system. And that one-electron is extremely far away from all the electrons and the nuclei. If you get to scale, you can think about that one electron as being in Pluto and all the other electrons being on Earth. So they're pretty far away. And if Sun is a nucleus. So now that one electron which is in Pluto behaves on its own. And it turns out that in ytterbium ion, that electron can be used as a storage of information. So it's a qubit. So you don't have a set of 7 or 8 electrons, qubits that are lying on a table. Instead, what we do is we take these ytterbium ions and put them in magnetic fields. And then we try to bring these ytterbium ions as close to each other as possible, as close as of the order of micrometers. Okay, so you got 2 ytterbium ions, which are micrometers apart. And then you try to address all of them together. And this addressing is like that flipping coin. So the ones, now imagine these ytterbium ions are each, so there's an up and a down state. Let's call it like the heads and the tails, and an up and a down state here. So you got up, up, down, down, up, down, down, up. So 2 ytterbium ions. Now, as they're flipping, they actually are flipping, right? As they're flipping, you try to interrogate them and you try to make them flip one way or the other. And this is called algebra. And this is how you do computation on a quantum computer, by using these magnetic fields and pulses to make them flip one way or the other.
Yeah, and we keep hearing about flipping coins and flipping ytterbium ions. That sounds very uncertain, and fundamentally we want computing to be certain. So how does the uncertainty map onto the certainty that we want in order to compute something? Jim?
Yeah, well, the notion is that classical computing is certain. And quantum chemistry, or the simulation that Srini talks about, those calculations are so complex that many times you have to make a lot of approximations to your problem before you solve them. You have to simplify a problem before it becomes tractable from a classical computer. Simplifying a problem means you might be causing uncertainty, you might be causing error, but the end result of that simplified simulation will be a difference between that and the actual result, or the accurate result. And so in many ways, classical computing is not certain in that sense. For quantum mechanics, there is kind of an intrinsic uncertainty for each simulation. And what you can do is to work around that is to run the simulation many times. And that's what we do today. That's what others do in the field. And then so you can get sort of an expectation value or average answer. And the hope would be that using a quantum computer, that answer would be more accurate than the answers from a classical computer done with many approximations or simplifications.
Okay, and Jim, your company and many others are investing an enormous amount in developing quantum computers. I think what everyone really wants to know is the exciting bit. I mean, what could quantum computing achieve in the coming decade?
In the coming decade, that's one comment is, if you look through history, it took 42 years from the first transistor to the first million transistor microprocessor, which came out, I think, in 1989 or 1990. And that was using Moore's law, or following Moore's law. So we have to temper expectations that we're not going to go from a few qubits to a million qubits overnight. That's going to take time. And so we do have to be patient. We're in the middle of an AI boom now, but AI has been around for a long time. It's just finally finding its footing, and quantum will be the same. So there probably isn't going to be one aha moment where one day there isn't a quantum computer and one day there is. To me, the applications that Srini talked about, protein folding is an example. A protein has something like 10 to the 80 different configurations, and only a couple of them are useful. And imagine if a quantum computer, you could understand what's happening biologically and come up with better treatments, better vaccines, better cancer solutions. That would be what would be really exciting to me.
And Srini, how is IU preparing for a future where quantum mechanics may be world-changing in terms of human health outcomes, understanding the weather, preventing disaster?
So there are many different ways in which IU is doing this. Now, one of the fundamental challenges that we're going to have is preparation of individuals who will be able to take on this new area. On the one hand, we are preparing young minds for a future in quantum by painting these analogies, which we hope will not require physics, will require logic. And that would be one way to develop a future quantum workforce. That's one idea. The other idea is in IU, we have, as you can also imagine, that this kind of an thought process cannot be from chemistry or physics or computer science. It's got to be all of the above. So I would say IU is very unique, apart from the fact that, of course, we are national champions, right, in football. Okay, that's not to downplay that in any small way. But apart from that, we are also pretty unique in the sense that we are one of the few universities where essentially there's a fantastic collaboration going on between chemistry, physics, and computer science and mathematics and so on and so forth, where These ideas are discussed on a daily basis. In fact, I have a meeting with a computer scientist immediately after this particular uh, discussion. So we are also coming up with methods that are asking questions like, when a molecule is undergoing some dynamics and it's got some spectrum in it, Carolyn Jarrold's area of research, spectroscopy. All right. When a molecule is undergoing some dynamics, is it also possible that it might be doing a computation which might be related to number theory? Does it have information in it that gets you the prime factors of some large numbers? So we think about molecules. Of course, they're quantum objects. So why not, right? Are they mapping complex arithmetic in them? Can you solve really hard problems? So, of course, this is coming up with collaborations with mathematicians and computer scientists and chemists and physicists, right? And then we are looking about new ways of thinking about chemistry to be modeling problems in other areas. And so, essentially, in IU, our thought process is very broad, and it encompasses many different areas. Additionally, IU is probably one of the few, Indiana is one of the probably few places where you have this industry university collaborative consortium. So IU, Purdue, and Notre Dame together are part of this National Science Foundation Center, along with 14 different companies, right, that are asking difficult questions in quantum, right, and trying to ask questions that might become interesting for industry. Right.
Can you tell me a little bit more about what it looks like to have this relationship with these various industries through the NSF-funded consortium?
Yeah, so I'm actually finding this to be very interesting. So our own collaborations are with people in industry who are mathematicians and computer scientists. And my own research is related to looking at molecules and quantum computers as graphs. So then I do computations and methods on these graphs. And a graph, for people who are uninitiated about it, you can think about Google Maps, right? Google Map is a graph. So now imagine that you want to go from here to Florida, all right? Google Maps gives you a very good route to go from here to Florida. And you have a set of vertices. So maybe Bloomington is a vertex, and there is a vertex at Louisville and Nashville and so on and so forth. And there are edges in this graph, the line that's connecting between Bloomington and Louisville and so on and so forth. But then, of course, there are many different ways you could go from here to Florida. Or what's the best way? Now, Google Maps is doing an on-the-fly computation to determine the fastest way to go from here to Florida, and it actually now is able to see traffic problems, blockages in the road, and stuff like that. But really, you can think about many different ways that that one can go from Bloomington, Florida. So molecule is exactly like that. You have a molecular dynamics, a chemical reaction that Jim was talking about. You're going from point A to point B. There are many different things that can happen at the same time. And the result is superposition. So we'll think about analogies to graphs, and then we now try to, once we've gone to the analogies of graphs, it's become mathematical. We can now connect many different areas into one. So our language is at the so-called meta level, where we connect many problems towards an abstraction.
So, Jim, tell us a little bit about what's really exciting you about the research that you're doing at Intel.
Yeah, spin qubits, again, are just like transistors. When you turn on a transistor, electricity or electrons flow through the device. And what we do is we design something that looks like a transistor. We operate at a very low temperature. Instead of a current or many electrons, a river of electrons flowing through the device, we have a single electron. And from a chemical sense, this is a single electron added into about 50,000 silicon atoms. So we're putting a single electron into that sea of silicon atoms, and we are controlling it. And it's very rewarding when there's something abstract like that where you can control the spin, the position of a single electron in a sea of that many silicon atoms. And when we are able to design our next quantum device to have multiple qubits, and it comes out of our large fabrication facility here in Oregon, it's very rewarding to feel like the work is deterministic in some sort of way.
And let's think a little bit more about what are the potential blue sky or stormy sky potentials for quantum computing. We're thinking material science design, artificial intelligence, encryption. What sorts of areas could quantum computing make a major impact?
First and foremost would be Shor's algorithm, which Peter Shor and I believe the 90s came up with the way of using a quantum computer of a certain size to factor codes. Currently, all of our email, credit card information is all protected by something known as an RSA key. And this is very hard to unencrypt or decrypt with a classical computer. It would take many supercomputers operating for hundreds of years to decrypt the information. A quantum computer of a certain size would be able to get that the information contained within very quickly. Now, depending on whether you play offense or defense, and Indiana was good at both this year, you either see this as an opportunity to know what your adversaries are working on, or as a risk to know that your information may not be protected. That's perhaps the first big application, and that's why every government in the world has some program on quantum computing.
And
Srini, your thoughts?
Yes, so that's a very important application, and we all have to be very careful about it because, of course, security and finances completely depend on that. There are other aspects that are extremely challenging. For example, when you talk about designing new drugs for cure of diseases. Now, from a more fundamental standpoint, if you look at biochemistry and the idea of protein structure, okay, so you have a protein is a sequence of little objects called amino acids, and each amino acid can be in a certain form. And so when you have, say if you assume that one amino acid can have two forms, right? And if you have n amino acids, then the number of forms, these are called conformations, is 2 to the power of n. It looks very much like the coin problem. Somehow nature knows how to choose one or a few out of those 2 to the power of n calculations very quickly, okay? And it does it in basically microscopic time. We still don't know how to do this. And of course, you can think about this. You can see it's a quantum problem because, again, you have an exponential scaling set of possibilities, and nature knows the correct answer. If we can find the correct answer reasonably quickly, perhaps we could make some impact towards diseases, right? So that's one area that quantum mechanics and quantum computing can have a role. The other is weather prediction, right? So we just had a major storm in Indiana with like about a lot of snow that we had to shovel outside. And I don't know about you, Jim. I hope you didn't have much snow, but then we had a lot.
Nothing this whole winter. It would have been nice to predict that at the beginning of the year.
That's exactly right. So the way in which the storms go, and it's a very hard fluid mechanics problem. And one has to solve a very complex differential equation for getting these answers. The reason we cannot do that is because if you imagine the entire Earth made up of a grid of points, those grids are probably about a kilometer away from each other. A kilometer is a long distance. Now, if you want to go from a kilometer to a meter, and now the number of grid points increases exponentially, it's a very, very difficult problem to solve. So these differential equations become hard. So there are lots of very difficult problems in engineering, chemistry, physics that all become now available for us to solve that will have impact in the future. More immediate impact, of course, Shor's algorithm.
would they alleviate the need for data centers?
So this is a very interesting question. So Jim talked about how we're constantly going to be in an environment where a quantum computer has got to be in the presence of a supercomputer because, of course, the supercomputer will have to now record, interrogate, look at the quantum system that's performing a computation, right? So the data centers will now take on that role where they are closely related to the quantum systems. But now you may also have quantum data centers, which now can store information in quantum states. Hopefully, if that happens, then we may have a huge compression of data requiring fewer data centers. But that's still a very open question because you could go the other way. If you ask that a quantum computer can do a lot of things at the same time, it can also store exponential information. And then that becomes an interesting question. So these are very hard, interesting research problems that people are working on.
Okay, so that's all the time we have today. Thanks very much to both of you for this conversation and your insights. I've really enjoyed this discussion.
Thank you.
Thank you. It was an honor to be here.
And thank you to our audience for listening. We hope you subscribe to the IU College Insider podcast. That's all for now.